In this problem, you are given the head of a linked list and tasked with deleting the middle node, then returning the head of the modified linked list. The middle node of a linked list of size n is the node at position n divided by 2, rounded down from the start using zero-based indexing. For example, for lists of sizes 1, 2, 3, 4, and 5, the middle nodes are at positions 0, 1, 1, 2, and 2, respectively. The challenge lies in efficiently finding and removing the middle node without traversing the list multiple times, which would increase the complexity of the solution. To achieve this, the algorithm employs a two-pointer technique. This method is efficient and elegant, allowing us to identify the middle node in a single pass through the list. The algorithm begins by creating a dummy node. This dummy node is a common technique used in linked list problems to simplify edge cases, particularly when deleting nodes. The dummy node is linked to the head of the list, acting as a placeholder that makes it easier to handle deletions at the head or other positions. The one pointer starts at this dummy node, while the two pointer starts at the head of the list. The purpose of using two pointers is to leverage their different speeds to find the middle node efficiently. One pointer moves one node at a time, while two pointer moves two nodes at a time. This differential speed is crucial because when two pointer reaches the end of the list, one pointer will be at the middle node. The idea is that by the time two pointer has traveled twice as many nodes, one pointer will have traveled exactly half that number, thus pointing to the node just before the middle node. Here is a step-by-step breakdown of the process. First, we initialize our variables. We start by initializing a dummy node. A new node is created and linked to the head of the list. This dummy node helps in manipulating the list more easily, especially during the deletion process. Next, we initialize two pointers. One pointer starts at the dummy node and two pointer starts at the head of the list. Then, we traverse the list. The algorithm uses a while loop to traverse the list. The loop continues as long as two pointer and the value in the node pointed to by two pointer are not null. This ensures that two pointer can move two steps ahead in each iteration. Then, each pointer has a specific movement. One pointer moves one step forward, while two pointer moves two steps forward. The next step is to identify the middle node. By the time two pointer reaches the end of the list, or has no next node, one pointer will be pointing to the node just before the middle node. This is because two pointer has moved twice as fast as one pointer. Then, we need to adjust the pointers. To delete the middle node, the next pointer of one pointer is adjusted. Specifically, the value in the node pointed to by one pointer is updated. This effectively removes the middle node from the list by bypassing it. Finally, the head of the modified list is returned by returning the value in the node pointed to by node, which points to the head of the list, skipping the dummy node. This approach ensures that the middle node is efficiently identified and removed in a single traversal of the list, making the algorithm both time and space efficient. In conclusion, this algorithm effectively uses the two-pointer technique to identify and remove the middle node from a linked list. By leveraging the dummy node and two-pointer traversal, the solution efficiently updates the linked list while maintaining optimal performance. The use of a dummy node simplifies edge cases, and the two-pointer method ensures that the middle node is found and removed in a single pass. Now, let's test this code to ensure it works as expected before submitting it. It's important to explore different algorithms and implementations to potentially find a more efficient solution. Testing with various linked list sizes and configurations will help verify the robustness of the algorithm.